So last week we were looking at appraising studies of interventions, specifically looking at two different kinds of statistics, the first known as descriptive and the second known as inferential. This week we're going to be talking about clinically relevant statistics. As I said before, there are really three categories of statistics. We've talked about descriptive and inferential last week. Now we're going to talk about the clinically relevant statistics, and these are the statistics that are really applicable to your patient population. Descriptive and inferential statistics can tell you something about how statistically significant the data is, but the clinically relevant statistics tells you whether or not you should apply this kind of result to your patient. So the rest of our slides presentation, we're going to be talking about clinically relevant statistics. Couple of definitions you need to know when it comes to clinically relevant statistics. Okay, the first one is called the point estimate. And the point estimate is just a word that means it's the single value that represents the true difference between the treatment and control groups. So, for example, if you can imagine a group of individuals that underwent the treatment, whatever that particular treatment was, versus individuals that they were compared to that were in the control group that did not receive the treatment, the difference, the estimate of the difference, the middle of the difference between those two groups would be your point estimate. Okay, another important definition to be aware of is a confidence interval. And just because you have the point estimate there, the confidence interval is the plausible range of differences within which that true difference resides. And that might be a little confusing, so I think the best way to explain it is to go ahead and show you an example. Okay, confidence intervals. You can think about identifying confidence intervals by as flipping a coin. Okay, if you toss the coin 2 times and you got one head and one tail, that's 50% of each, that means that your point estimate is going to be 0.5 or 50%. You really can't be 95% confident that 50% is really what's going to happen every time, right? Since your real confidence interval, or the number that can be real with only 2 tosses, is anywhere from 0.01 to 0.99 for 95% confidence. And for 95% confident, you'd have to span from 0.03 to 0.98. Okay, go on down to if you toss the coin 50 times. Well, in 50 times, you just happen to get 25 heads and 25 tails. Your point estimate is still 0.5, but since you've tossed the coin that many more times, you can be 95% confident if the number is between 0.36 and 0.65. Okay, now you can be 90% confident that that real point estimate is between the values of 0.38 to 0.62. Now, all the way down, if you toss the coin 1,000 times, you got 500 heads and 500 tails. Okay, your point estimate hasn't changed. However, your 95% confidence interval is now the same as your 90% confidence interval. And you can be 95 or 90% confident that that point estimate resides between the values of 0.47 to 0.53. Okay, so the larger your sample size, the more confident you can be that that point estimate resides within that confidence interval. Okay, moving on to statistically significant versus clinically meaningful. 0 represents the line of no difference on the x-axis, and you can either have something that has a negative effect, which is on the left side of 0, And then you can have positive effects that are on the right side of 0. Okay, now if you look at the p-value is something that you've derived from your inferential statistics. We've learned that if p is less than 0.05, then the result is statistically significant. And if you look on the right of the 0, you can see your confidence interval is far, far to the right of 0. So this would have clinical significance. Okay, if it were crossing 0, it would have no clinical significance. So just looking at the first line, you can see that you have statistical significance as well as clinically significant effects. Okay, moving down to p less than 0.05, this is still statistically significant, but the line is getting closer to 0. So you have statistical significance, but there's not it's not really clear whether there's a significant clinical effect. Okay, so the line's getting closer to 0, so it's not a huge clinical effect. So there's really not very much difference whether you're in the treatment group or the control group here. Now, moving one down, when it says N period, S period, that's not significant. Okay, so there P is greater than 0.05, so you have not a statistically significant result, and the confidence interval crosses the line of no difference, or the 0 value. So it's completely inconclusive. We have neither statistical significance nor do we have clinical significance. Okay, moving down, again, we have not statistically significant, so p greater than 0.05, but the confidence interval margin is definitely crossing the line of no difference, or the 0 value. So this is neither statistically nor clinically significant. And if the last point is p less than 0.05, this is statistically significant reverse effect, means that you have statistical significance, but you clearly have no clinical meaningfulness for your patient. So this is something that we'll look at as we move forward, specifically when we look at different meta-analysis, and you're always comparing whether something's statistically significant versus clinically meaningful. Something can be statistically significant and not have any clinical meaningfulness at all. So that's the importance of looking at that point estimate versus the confidence interval. Another definition that you need to know is something known as an effect size. An effect size is also known as Cohen's d. Okay, on the table on the right, you can see I've listed different values here, which are pretty standard values for Cohen's d, and the interpretation that you can make if you see a Cohen's d with this approximate value. So, if you see a Cohen's d listed as 0, you can be assured that there's no difference between experimental and control treatments. Okay, if Cohen's d is 0.2, there's going to be a small difference. 0.5 is considered a median difference, and you should know that greater than 0.8, having a Cohen's d of greater than 0.8, that you would expect a large difference in effect of experimental versus the control group. Okay. This is important. This is something that you want to be aware of, and it's going to tell you whether or not you want to use a treatment for a particular patient. The larger the effect size, or the Cohen's d value, the more likely that treatment, when done correctly, is going to have a large effect, positive effect on your patient. Okay, the last definition that you need to know about is abbreviated NNT. It's really called the number needed to treat. Okay, it's really just an effect size estimate. So the best way to say it is to look at the example on the bottom. The NNT is equal to 10. This simply means that for every 10 people treated, at least one person would have a better outcome than if they weren't treated in this way. Okay, so if you're doing treatment and that treatment is predicted to have an NNT of 100, then 100 people would have to be treated for only one to have a positive effect. So the higher the NNT, the less likely you are to want to use that treatment with a patient. The smaller the NNT, the more likely you would be to use that treatment for a particular patient.